Over the last decade, a lot of things have changed in software development, such as moving a lot of data around, the volume of data being produced and handled, size of deployments, faster release cycles, achieving 100% availability, millisecond response times, cloud based clusters, resiliency, and elasticity. And to achieve all this, we need a system which is very responsive, resilient, elastic, and message driven. And with reactive programming, you can achieve all these functionality and you can build a enterprise grade reactive system. There are four reactive principles: responsive, resilient, elastic, and message driven. A reactive system is responsive when it is responding to the request in a timely fashion, and this is the primary goal of the reactive principles. A system is resilient when it is capable of handling errors. In case of errors, reactive systems responds to its listeners, and the inclusion of back pressure in the reactive programming ensures better resilience between decoupled components. Failures are isolated into a single component, and in case of failures, the external component does recovery and replication ensures high availability. Your system should be capable enough to auto-scale in peak hours to handle the increased load. And the elastic principle of reactive programming fulfills it. Predictive auto-scaling technique can be used to support elasticity. The fourth principle is message driven. A reactive system acts on triggered events and it fits very well in message driven architecture. Since messages are asynchronous and non-blocking, so they provide loose coupling, isolation, and location transparency. Reactive programming can be used to build reactive systems. It breaks problems into small and discrete steps. Steps are executed in asynchronous and non-blocking fashion using a callback mechanism. Reactive application is a combination of functional programming, event-based programming, loosely coupled, and error resilience. So before moving on, let's understand what is synchronous and blocking. In a traditional app server, when a request reaches to the server, it is executed on a main thread. And if there is a database call or REST API, then this thread will be waiting until unless it gets the data from the database server or from the HTTP server. So this main thread is blocked on the IO level. And as far as the application server get more requests, more threads are created and blocked, and our application will start rejecting further requests. So how can we solve this problem? The first solution is that we can make asynchronous calls to database and HTTP servers by creating a new thread. By this way, we can get the data asynchronously and parallelly. But these new threads still be blocked on the IO level because they are still waiting to get the data from the database and HTTP server. Also, creating a new thread is very expensive. Let's see how this problem can be solved using the reactive server, which offers asynchronous and non-blocking IO. A reactive server processes the request in an asynchronous manner. There is an event loop mechanism which accepts the request and delegates it further to the worker threads. And to understand, event loop is a non-blocking IO thread which runs continuously and takes new requests. Let's understand how event loop works. As you can see in the diagram, event loop is taking a request via a socket channel and then delegates it to the worker threads. Worker threads further processes the requests, executes your application code, which can be intensive, such as processing a file, getting data from database server, or some other computation. After completion, worker thread writes the response to a task and adds that in scheduler task queue. Event loop keeps polling the scheduler task queue, and as soon as it gets a task from it and handed back the response to the same socket. And there could be 4 to 5 event loop threads in a reactive server based on the CPU cores. Event loops keep running forever, accepts the request, and then delegates it to a worker thread whenever there is a new request, and the cycle goes on. So nothing is getting blocked on the server side, but we still have the IO blocking issue on the database and HTTP calls level. And to solve that, Reactive Library offers a non-blocking web client to make the HTTP calls asynchronously. And to solve the problems of blocked database call, there are R2DBC drivers which are non-blocking in nature. Like I said earlier, reactive programming is based on a publisher-subscriber model. In this model, publisher is potential source of data and subscriber subscribes to it through a subscription. After subscribing, subscriber demands for data and publisher publishes the data to a request method. On base of subscribers consuming capacity, publisher streams the data to its subscribers. This model uses a backpressure technique to control the data flow in case a subscriber is not able to catch up the speed of a subscriber. Publisher passes the signal to its subscriber if there is an error in between or stream is completed. It has a very good support of resiliency where you can handle your exception in a reactive stream, you can propagate your exceptions, or you can start a new stream if there is any error in the previous stream. Reactor API has two publisher types, Mono and Flux, where Mono contains only one element and Flux contains n number of elements. Publisher can be created by calling the just method. Like in this example, if we want to create a mono of string, we can use mono.just and pass our string value to it. If you want to create a flux, then you can pass multiple value to its method. By using this publisher, you can create your reactive stream. You can add operators to it, exception handler methods, and you can convert your stream to another stream. As in this diagram, you can see the life cycle of a mono. We can create a mono by adding some optional values in it. Then we can add operators which used to transform the data. And there could be a case when your mono is terminating with an error. On the other side, Flux can contain n number of elements. As you can see in this example, there are 6 elements in the Flux which are being processed sequentially. You can add operators in between, and if your Flux is terminating with some error, then further elements will be dropped and there will be no further processing. And later in this course, we will be learning how we can handle these exceptions, how can restart our stream, and how can we add retries, circuit breakers, and other operators.